Okay, we're going to talk now about the gas transport. Okay, and let's go over here. Okay, so now this is really about the pickup and the delivery of the gases. Blood carries the gases to the body tissues as well as storing them. What about oxygen transport? And then we'll look at CO2. Oxygen, most of the oxygen molecules bind to hemoglobin. Hemoglobin, we know, has 4 subunits, and when one molecule of oxygen binds to one of the ions, then the other 3 ions have more affinity for oxygen, and this is called cooperative bonding. Okay, so there's a special specificity to the ion by the oxygen. So as soon as one oxygen binds, the other ions have a greater capacity or affinity for letting the oxygens bind to their ions. So the bond of hemoglobin with oxygen is a reversible bond. The hemoglobin carries the oxygen and then it releases it to the tissues where it is needed. The amount of oxygen that is released or retained in the blood will depend on 3 factors. It depends on the partial pressure of oxygen, the pH of the tissue, and the temperature of the tissue. What about the partial pressure of the oxygen? Well, if the oxygen content of a tissue is low, then oxygen will be released by hemoglobin as the blood circulates through this region. The pH. Active tissues generate acids. That causes the pH of the interstitial fluids to decrease. So they're more acidic. So hemoglobin is going to release more oxygen. Now, hemoglobin is also involved with carrying a buffer called bicarbonate, but we'll see that very shortly. In any event, temperature. When the temperature increases, okay, hemoglobin releases more oxygen. These effects are well exemplified, that is, partial pressure of oxygen, pH, and temperature, in active tissues. When skeletal muscles, for example, work very hard during exercise, their temperature increases, but the pH and the partial pressure of oxygen is going to decrease. Therefore, when the hemoglobin circulates in the blood, okay, it's going to release larger amounts of oxygen to this tissue, and this is an automatic adjustment. What about carbon monoxide poisoning, CO, that is in the auto exhaust, oil lamps, and in fueled space heaters? Okay, nowadays cars, their motors are so quiet that people pull into their garages, they think they turned off their car, or they paid no attention, they close the garage door, they go upstairs, they make dinner for the children, okay, and then all of a sudden the next day, everybody's gone, goodbye, because they left the motor running and CO has no smell. So that's why now carbon monoxide detectors have become very common. You should put one in your garage, you should put one in your entry foyer, and probably near the bedrooms, because people today, I included, the motors are so quiet, you think you turned it off, but you really didn't. And if you put your car in your garage, it's gone, goodbye, okay? All right, CO2 transport. This is kind of interesting. CO2 is generated during tissue metabolism, and it enters the blood. 7% will dissolve in the plasma. That is not shown on this picture, but if you turn to page 87 and 88, okay, you can see my picture does show some of this. Okay, 7% of the, well, this is not shown, but 7% of the carbon dioxide will dissolve in the plasma. 23% gets into the red blood cell and binds to hemoglobin, forming carbaminohemoglobin. Okay, carbaminohemoglobin. And this is going to be released into the pulmonary capillaries, okay? So this is on page 87. 7% goes into the plasma, 23% goes into the red blood cell to form carbaminohemoglobin, and this then is going to be released into the pulmonary capillaries. The other 70% of carbon dioxide is interesting, and we can see this in the picture that I've done for you on page 88. And you can see that what happens is the carbon dioxide is going to combine with water to form carbonic acid, H2CO3. Now, the carbonic acid, okay, is going to give up a hydrogen or a proton to hemoglobin because it's a buffer. And so we're left with bicarbonate that will go into the plasma where there's a sodium and form sodium, well, it should be sodium carbonate, okay? Sodium carbonate is traveling in the plasma. But now when we get back to the lungs, okay, the sodium carbonate will give off again the sodium and the proton will be released. And so we have back again our bicarbonate, and that will then be transformed into the CO2, which will be eliminated because what happens is the bicarbonate goes back into the red blood cell. When we get to the lungs, it leaves the plasma in the form of, it was in the form of sodium carbonate, but it goes back into the red blood cell, and then it's going to be released to the air because the reverse reaction is going to occur. Okay, so the carbonic acid is formed, and then it actually breaks up again. And so in this way, we can release the CO2. So most of the H2CO3 forms the bicarbonate, and you can see then my picture is showing you in the top portion what's going on in the red blood cell, and then you see the little box inside showing you how the proton goes to the hemoglobin portion, okay? And then you can see how the bicarbonate goes in the plasma until we get to the lungs where it goes back into the red blood cell, and then it can be released as CO2, okay? All right, so some of the bicarbonate will go into the plasma. Most of it undergoes this reversible reaction with the formation of the, under the effect of carbonic anhydrase to form carbonic acid, and some of it forms this carbaminohemoglobin, okay? All right, the next portion is the last portion, and it's going to be about respiratory control. How is respiration controlled, okay? And so as soon as I get this iPad to give me the right response, I can continue. But we are going to talk now about that. All right, respiratory control. Now, let's go there. This is just showing you here. This reaction is much more complex looking at it here, but I think if you use my picture, it's a little clearer, okay? Okay, oops. Now I want to go screen share again. And I want to go to a different, sorry for all this technical business regulation I want to go to, but anyway. I'm just sitting here having a party. I'm talking all to myself. Stop share, okay, windows closed. I hope the screen share is back on again now. It should be. Okay, so normally the rate of cellular oxygen absorption and CO2 generation matches. In other words, O2 delivery matches CO2 removal. If the rates become unbalanced, the cardiovascular and the respiratory system must readjust. And we have the respiratory center, which is part of the reticular formation of the medulla and the pons, which we'll learn about when we talk about the nervous system. But in any event, the respiratory center regulates the respiratory muscles. It controls the respiratory rate, which is the number of breaths per minute. And a normal adult at rest we take between 12 to 15 breaths per minute. You can count them if you don't believe me. The respiratory center also controls the depth of breathing. So it controls the respiratory rate, the depth of breathing, and it regulates the respiratory muscles. Now we have the respiratory rhythmicity center, which is in the medulla, okay? And this sets the pace of breathing, and there are two subdivisions. There is the inspiratory center, and there is the expiratory center. Okay, you can see here an inspiratory center and an expiratory center. Okay, now there's also respiratory centers in the pons, okay, higher up. And these are called the pneumotaxic and the apneustic areas, okay, the pneumotaxic and the apneustic areas. These control or adjust the rhythmicity center below. So this is a higher level of control, okay? The respiratory center in the pons responds to sensations and emotions, and it controls and adjusts the lower rhythmicity center. Let's take a better look at how the rhythmicity center works in breathing, okay? And you have a nice table here, okay? So during the rhythmicity center, if we look at the inspiratory center and the expiratory centers with regard to quiet breathing, okay, in normal inspiration and expiration, okay, the active portion is when we have the stimulation of the inspiratory muscles for 2 seconds. This includes the diaphragm and the external intercostals. They are the inspiratory muscles. Then there is silence for the next 3 seconds, so the muscles relax, and we have passive exhalation, okay? So the expiratory center is inactive during quiet breathing, okay? Active center is stimulating those muscles for about 2 seconds, and then it's silent for 3 seconds. So the quiet breathing is controlled automatically to maintain a basic rhythm. What about enforced breathing? Well, the inspiratory center becomes active, okay? And it stimulates the accessory muscles, that is the sternocleidomastoid, the scalenes, and we saw also the pectoralis major. Besides the diaphragm and the external intercostals, besides those that are normally working in the active, regular, quiet breathing, you have sternocleidomastoid, scalenes, and pectoralis major, besides the diaphragm and the external intercostals. And that is for the forced inspiration, okay? Forced breathing now with the expiratory center is also active. We have the stimulation of the accessory muscles that are involved in exhalation, and this time in this type of exhalation, and this is with forced exhalation, and this involves the abdominal obliques and the abdominal transversus, okay? So this is important to understand what's going on with inspiration and expiration with regard to the respiratory center. Again, as I said, the pneumotaxic and the apneustic areas are a higher control over these lower areas, but these are the inspiratory and expiratory areas. We'll see more about how these work when we get to the physiology of the nervous system. I don't want to get into too much of that now. Okay, so this is showing you here basically what I just talked about, okay? Inspiratory area, active in normal inspiration, okay? And then inactive for 3 seconds in normal expiration. Okay, this is during quiet breathing, and then during labor breathing, this is the table. This is similar to what I drew. One more point to make. These respiratory centers can be affected by, 1, elevated body temperature, and central nervous system stimulants like amphetamines and caffeine. Both of these factors, that is an elevated body temperature and CNS stimulators, will increase the respiratory rate. So when you drink coffee, okay, or when you take amphetamines, like methamphetamine, okay, or smoke it or inhale it, Tina, you know what I'm talking about? Okay, the respiratory rate increases. When we have a decrease in body temperature and central nervous system depressants, such as barbiturates and opiates, which you take for pain, for example, they would decrease the respiratory rate. So I suppose you could take a opioid for pain and then have a cup of coffee and you will stabilize yourself. But I don't suggest doing that kinds of things. But anyway, there's much tighter controls now, as you know, in Florida on obtaining these narcotic prescriptions. So we just need to learn that there are stimulants and there are depressants to the respiratory system. Okay, that concludes the respiration system, the respiratory system, and there'll be further instructions in the modules as to what you need to do, okay? I don't think the rest of this is, we need to get into any of this. This is too much detail for us, but okay, that's all we're gonna do here. So that will end our recordings now.